In section 6.3, we're going to look at the second application of derivatives, and that being optimization problems. Now, optimization problems are sometimes referred to as max-min problems, and there are many real-world applications of these types of questions. What I'm going to do is I'm going to start off with a number example, and this example or this type of problem is going to set the foundation to do all the other optimization problems. So we have, we're asked to find two non-negative numbers whose sum is 15, and the product of one number with the square of the other is a maximum. Okay, there's a lot going on here, so let's start. First of all, we want to find two non-negative numbers, so we need two variables. I'm going to let x equal the first non-negative number, and y equal the second non-negative number. Okay, so now we want to develop two equations. The first equation is quite easy. It says the sum of these two numbers is 15. So x plus y is equal to 15. And the second equation comes from the second statement here that says the product of one number with the square of the other is a maximum. I don't know what the product is, so I'm just going to call that product is equal to, well, it's one number with the square of the other is going to be a maximum. So eventually, this is the one that I want to maximize, the product. So therefore, this is the one that eventually I'm going to have to take the derivative of. The problem is, I have two variables in this product, and I want to try to get it in terms of one variable. So what I'm going to do is I'm going to go to my first equation here, and the easiest variable to get by itself in this equation is x. So I'm going to isolate x by itself here and say x is equal to 15 minus y. And then I'm going to take that and substitute it in place of x. So therefore, when I do that, my product is going to equal, in place of x, I'm putting 15 minus y times y squared. If I multiply these together, I get 15y squared minus y cubed. So there I have my product in terms of y. Now, just like before, to find the maximum, I want to take the derivative. So the derivative of this is going to be 30y minus 3y squared. And I want to figure out what makes the derivative 0. I don't need to worry about what makes it undefined, as it's a polynomial. So I set the derivative to 0. And I could factor a 3y out, and I'll be left with 10 minus y. And my two possible answers, 3y equals 0 when y is 0, and 10 minus y equals 0 when y is equal to 10. So those are my two critical numbers. So my absolute or my relative maximum, or my maximum, is going to happen at either when y is 0 or y is 10. So now we have to decide which one we use. Well, there's two ways we could do this. Number one, we could use our number line test like we did in the last chapter. So I could take my two critical numbers, and I could test them in the first derivative. And the first derivative in factored form is right here. So I'm going to test numbers to the left, of 0, like let's test negative 1. I'm going to test 5, and I'll test 11. If I put a negative 1 in this guy, he's negative. A negative 1 in here is positive, and a negative times a positive is a negative. 3 times 5 is positive, 10 minus 5 is positive, that's going to be positive. And 11 is going to be positive times a negative, it's going to be negative. And now we want to look for a relative max. Well, the relative max happens where the derivative changes from positive to negative, that's supposed to be 0. So it's changing at 10. So I get a maximum at x or y equals 10. And this is my proof to prove that y equals 10 is a maximum. So I found my first number. Now I need to find the other number, x. So if I go back to this first equation, I have x equals 15 minus y. So x is equal to 15 minus 10. So therefore x is equal to 5. In your final statement, you're going to say the two numbers are 5 and 10. So basically what it means is if I look at my product statement, the product of one number, which we said was x, times the square of the other, the maximum product I could get of two numbers that add to be 15, and one of them multiplied by the square of the other. If I took all the combinations of numbers that added to 15 and plugged them into this product equation, my maximum formula would be, or my maximum product, make that look like a 5, would be 500. Okay, so that's kind of the framework of how we do max-min problems. Develop two equations, use one equation to eliminate a variable in the other one, take the derivative, find the maximums, or the critical numbers for, and then find whether the critical numbers are max and mins, and then answer your question. In the second example, I'll show you a second way to find whether these are max or mins without having to do a number line test. So the next type of problems are area perimeter problems. And if we take a look at this question, it says that we have a conservation park. A lifeguard has 620 meters of rope to rope off a rectangular safe swim area. One of the sides of the safe swim area is going to be the beach, and you want to calculate dimensions that will maximize the swimming area. Okay, so let's try and draw a picture of the situation here. So here's the sand, and then we have our water out here, and we want to use all of our rope to make a safe swim area in the shape of a rectangle. So I'm going to use the rope like this and form a rectangle. Obviously I wouldn't run the rope along the beach because the beach is acting like a natural barrier. So I need a couple of variables. I'm going to let W equal the width and L equal the length. Now, it says that I have 620 meters of rope. Well, I want to use up all of my rope, so if I add up my three sides, which is 2W plus L, that has to equal 620 meters. So there's my first equation. And I want to maximize the swimming area. So the area of my rectangle is length times width, and this is the one I want to maximize. So that's the one I'm going to have to take the derivative of. Problem is I have two variables. If I look at my first equation, I can isolate L very easily. So I'm going to subtract 2W. I'm going to plug the 620 minus 2W in for L into that area equation. And this works out to be 620W minus 2W squared when I multiply those together. So now I have to take the derivative. So A prime is going to be 620 minus 4W. Now I have to find the critical number, so I set this equal to 0. Add the 4W to the other side, and then I just have to divide both sides by 4W, so 620 by 4, sorry. So W works out to be 155. Now we want to prove this is a maximum. Okay? Well, you know what, I'm going to do the number line test here again. I'll show that other method in a question later on. So I'm going to use A prime, and my only critical number was 155. So let's use 1 and say 200 as my test points. If I put 1 into the derivative, that's going to be positive. If I put 200 in here, 620 minus 800 is going to be negative. Therefore, we know that W equaling 155 is a maximum because my derivative is changing from positive to negative. So now I need to find L. So L, if we look back at our first equation, was 620 minus 2W. So it's going to be 620 minus 2 times 155. And if you work that out, it's 310. Now, let's answer the question, because sometimes they might ask you for the maximum area, which you'd have to plug in here to find. but they're just asking us calculate the dimensions that will maximize the area. So I'm really done the problem, just my final statement, and make sure you include your units in the final statement. So you would say the dimensions of the safe swim area are 155 meters by 310 meters. And that would be your last step. Okay, we'll take a look at one more example. And this one is saying we have a farmer who wants to build a 216 meter squared rectangular garden. And then they want to divide it in half using another fence parallel to one side. What dimensions for their outer rectangle will require the smallest amount of fencing? So we want the dimensions and how much fencing should be used. So we have to look for two answers here. But let's draw a diagram for the situation. First of all, we have a rectangular garden. Has some width and has some length, and it also wants us to cut this in half using another section of fence. So these are all representing sections of fence. So I have 3 widths and I have 2 lengths, and the length is going from one edge to the other edge. And we know the area of this garden is 216. So to figure out the area is simply length times width, and I know the area is 216. So there's my first formula. Now, we want to know the dimensions that will require the least amount of fencing. So I want to find really the perimeter, or add up all the sides of this fence. So the fence is going to be 3 widths plus 2 lengths. And I want to minimize the amount of fence. So this is the one I want to take the derivative of. But the problem, again, I have 2 variables, so I'm going to isolate one of them. I'm going to divide by L, so therefore W equals 216 over L. So I'm going to place that in there. So I get 3 times 216 over L plus 2L. And if I multiply 216 times 3, I get 648. And I'm going to move that L up to the numerator, so it becomes L to the minus 1 plus 2L. Now I have it ready to take the derivative. So now to figure out f prime, I bring the negative out front, so negative 648 L to the minus 2 plus 2. And that is the derivative. So if I rewrite this, this is negative 648 over L squared plus 2. That's my derivative. So I'm going to figure out what makes the derivative 0 and what makes the derivative undefined. Well, the value that makes it undefined is when L is 0, but we can't have a 0 length, so that one's admissible. To figure out what makes this equal 0, I'm just going to set the whole equation, or the whole derivative, to 0. I'll add my fraction over to the other side. Multiply both sides by L squared. Divide both sides by 2, and I get 324 is equal to L squared. And if I square root both sides, I will get plus or minus 18 is equal to L. Again, we can't have a negative length, so the only possible critical number that could be a minimum is when the length is 18. So now I want to do my proof, and this time I'm going to use what's called the second derivative test to prove whether a critical number is a max or a min. And here's what it says. If I take my critical number, which is 18, and plug it into the second derivative, if it makes the second derivative positive, then my graph is concave up, and my critical number has to be a min. If the critical number plugged into the second derivative is negative, then the second derivative negative is concave down, and then my critical number is going to be a max. So if I'm going to do the second derivative test, I have to take the second derivative, so f double prime. The negative 2 comes out in front, and 648 times 2 is going to be 1296. L to the minus 3, and I'll just move it down to the bottom right away. And the derivative of 2 is 0. Now, if I take the second derivative and evaluate it at my critical point of 18, I get 1296 over 18 cubed. This is going to be a positive number. So that means my graph at 18 is concave up, which means my critical number is going to be a horizontal tangent at the bottom. So therefore, L equals 18 is a minimum. So I found my length. So now we have to find the width. And to find the width, I can use this equation right here. So the width equals 216 over L, which is, 216 over 18. And if I take 216 and divide it by 18, I get a width of 12. So I know the dimensions are 12 meters by 18 meters, and now I also want to find the minimum amount of fence, so I just plug those values into my fence equation. So it's 3 times 12 plus 2 times 18. 36 and 36 is going to be 72 meters. So my final statement, the dimensions, and I guess this should be the outer dimensions of the garden, are 12 meters by 18 meters, and the least amount of fence is 72 meters. And that would be the end of the first part of optimization problems. So there are a few questions for you to try. Now I'm going to eliminate some of these because we don't need to worry about the number problems too much, because we just set the foundation of how to do these questions. So I am going to eliminate a couple of these. Okay, so you can try question number 2. Don't worry about 3, don't worry about 5, 7, or 9. And then we have 11, 12, 13, and 14 are some of our area perimeter problems. So you have 5 questions there to try. The answers are posted on the webpage. If you have any questions, feel free to send me an email.